In this module, we will discuss the building blocks of analog electronics, which are the operational amplifiers. These are the objectives of this module. First, we'll examine how an op-amp is physically constructed. Second, how do we represent an op-amp in a circuit? We will describe the characteristics of an ideal op-amp. Um, we'll demonstrate what is a non-inverting and inverting amplifiers, and we'll show some examples how to handle op-amps. But what are amplifiers? So amplifiers are devices that simply magnifies the signals that goes through it. It consists of an input. So let's say this is our amplifier. Okay. So it consists of an input. So a signal goes through the input. So let's say this is X. And that is signal is processed and comes out at the output where it becomes a magnified representation of the input signal. So where A there is the gain of an amplifier. So this amplifier is what we call a gain. So what are op-amps? So op-amps are a type of amplifier that can do several operations like addition, differentiation, and integration of signals. They consist of a complex arrangements of several elements like resistors, transistors, capacitors, and diodes. And they are the building blocks of analog electronics. So our consumer electronics consist of several op-amps that are crucial in the operation of these devices. An op-amp is represented by a triangle in circuits. So the symbol has two input terminals. We call the inverting input and the non-inverting input. It also has an output terminal 6. Sometimes we draw the op-amp along with other terminals, like for example terminals 4 and 7, which represents the power supply terminals. Um, in addition to that, sometimes we also see terminals 1 and 5 that are used for offset. But the most important terminals here are the terminals 2, 3, and 6. And we always see them in the analysis of op-amps. An op-amp comes in an IC package or an integrated circuit package. So here we have a 3D representation of that IC package using the 741 8-pin dual inline package. This particular package has a single op-amp, so as seen in the drawing of the IC, with the terminals clearly connected to the outside pins of the IC. As mentioned, an op-amp has two inputs. We have the inverting and the non-inverting. So what is the difference between these two inputs? When I apply a signal to a non-inverting input, let's say I feed this with positive 1 millivolt, I could get here, let's say, positive 1 volt. So that is an amplification of 1000. So if I feed a positive signal in the non-inverting input, I also get a positive output, an amplified version of the input. But when I feed that same signal to the inverting input, I also get an amplified version, but this time it will be the reverse of the input, so it comes out negative 1 volt. Okay, an op-amp is an active element, so meaning it requires power supply. And the way to connect the power supply is shown in this figure. Terminal 7 is connected to a positive supply, while terminal 4 is connected to a negative supply. So meaning there must be a ground potential. So here in this drawing, we connected two supplies in series, and the node between them is connected to ground to provide the positive and the negative voltages. As mentioned a while ago, an op-amp is a complex circuit, so we won't discuss the details on how this uh, element is constructed or designed, but we simply look into its equivalent circuit so that we will have an idea of its behavior. So again, this is the symbol of an op-amp, and the input is represented here. So this is the input. It consists of the two terminals, as mentioned, the inverting and the non-inverting terminals. And these terminals are um, separated by a resistance R sub I. So terminal 2 is the voltage at terminal 2 is V sub 1 with respect to ground, while the voltage on terminal 3 is V sub 2 with respect to ground. The difference between the potential difference between these two input terminals is what we call the voltage V sub D, which is defined as the potential of the non-inverting terminal minus the potential of the inverting terminal. The output section of the equivalent circuit is represented by a dependent voltage source, which has a magnitude that is dependent on the voltage difference between the two input terminals. And terminal 6 is represented by the potential V naught with respect to ground. Um, at no load, I sub naught is equals to 0, while V naught is equals to the voltage of the dependent voltage source, where A there is what we call the open loop voltage gain. The output terminal is connected to the dependent voltage source through an output resistance R sub naught, which is usually a very small resistance compared to R sub I, which is a very high resistance. These are the typical values for the different um, parameters of the equivalent circuits. For the open loop gain, this is usually very high and ranges from 10 to the fifth to 10 to the eighth. The input resistance is also very high, so it is given in this range. The output resistance, as I mentioned, is very small, and the supply voltage of the op-amp usually ranges between 5 and 24 volts. Now, sometimes we use ideal values for these parameters. For the open loop gain, we usually assume that to be infinity, same with input resistance, while for the output resistance, we usually assume that to be a zero resistance. Here we have an op-amp where the non-inverting terminal is connected to an input signal, P sub S, and the output is connected to a load. This configuration is what we call an open loop system because the input and the output are completely separate or independent. They're not connected whatsoever except for the grounding. Well, we usually don't use an op-amp this way because the output tends to be very unstable due to variations of the gain, the open loop gain. Normally, we use the op-amp using a feedback configuration. So here is an example of a feedback configuration. In here, we see a negative feedback connection where a sample of the output is feedback to the input, specifically to the inverting terminal of the input. We can also create a positive feedback if, for example, we instead of connecting the output to the negative terminal of the input, we don't do this, but let's say we connect it uh, like this. So uh, we feedback some of the output to the non-inverting terminal of the op-amp, so that creates a positive feedback configuration. The ratio of the output V naught with the input Vs is what we call the um, closed loop gain of the feedback system, or the closed loop gain. So V naught over Vs is the closed loop gain. Let us have an example to illustrate how to handle an op-amp in a circuit using the feedback configuration. Here we have a 741 op-amp with an open loop gain of this one. Okay, so this one is our A, and an input resistance of 2 mega ohms. So this one is our R sub I, and output resistance of 50 ohms. So this is our R sub naught. We are required to compute for the closed loop gain and as well as the output current, assuming we have an input voltage of 1 volt. So in solving the problem, we use the equivalent circuit of the op-amp. So this is the equivalent circuit as enclosed by the dotted line with the external elements also connected. Now, usually when we solve uh, problems involving op-amps, we extensively use nodal analysis. So to solve this using nodal analysis, first we identify the nodes that we will use to create KCL equations. So here, these are the nodes V sub 1 and V sub naught. I've also indicated the direction of the branch currents uh, towards or away from the nodes. So these are the KCL equations. So at node V sub 1, current entering, so this one is entering equals current leaving. Uh, so doing some rearrangements, we can get equation 1. We can also write KCL equation at V sub naught. So current entering again, which is this one, is equals to current leaving, which has this current and this current, which is this one and this one. So rearranging the equation, we get equation number 2. Combining the two equations by dividing them, we get a single equation, and from here we can get the ratio V naught over Vs. Uh, for an input voltage of 1 volt, that should give us an output of 9 volts. So the output is 9 times higher than the input, and it is positive because the input is connected to the non-inverting terminal of the input. Given the output, we can solve for the node voltage V sub 1, and from there we can also solve for I sub naught, which is by KCL equals to this current plus this current. This current is this one, while this current is this one, and that should give us this value.